All right, so in this exercise, we're going to be estimating the actual value of a number pi, which represents the ratio between the area, or the circumference and the radius of a circle. And the reason we're saying that we're estimating it is pi is a repeating number. There is no exact value to it. So 3.14159 is the first 5 digits here, but pi will keep repeating out, or it's actually a non-repeating sequence of decimal values, theoretically out to infinity. So it's not something that we can get a precise answer on, but what we're going to try to do is numerically try to get as many significant figures as we can. And so uh, one way to do this, and there are a variety of ways that computers can get a more and more accurate number for pi, but one way is through simple summation of a repeating series of fractions. And so the idea is to take this series, which can repeat indefinitely, so we can have or continue indefinitely. So the next number in the sequence would be a positive 1 divided by 13, and then subtracted by a 1 over 15 and a 1 over 17, and on and on and on. So you can certainly see that a computer has the potential for calculating lots and lots and lots of these terms using a simple loop. So we're going to write a program to do this, and I'm going to have the user actually type in how many terms in this sequence we're willing to use. And then we'll see what the actual value is after each term. Of course, if the user types in one term, it'll just be that one, and the computer's estimate for pi will be 4. If they type in 2 terms, we'll have the 4 times 2/3, right? So we're going to be kind of actually bouncing. We'll be above pi with just 1 term. We'll be below pi with 2 terms, and we'll be back above. And the actual value should sort of bracket the true value of pi alternating. So our first step is to figure out sort of how do we generate a pattern? How do we generate this computation? And so I'm going to switch over and draw the I'm going to draw the actual formula a couple of different ways. First of all, I'm going to forget about the 4. So we're multiplying by 4 at the very end. I'm much more interested in computing this. This is the harder part. And if you think back about the other exercises where we printed out a repeating sequence of stars or something like that, it's very much the same exercise. We need to generate these terms. Okay, so if we switch over here, we have 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11. And we notice certainly that there is some sequence here. There's some pattern with the denominator, and there's an alternation of whether or not we're doing plus or minus. Now, when we're trying to devise a loop, again, and we've talked about this a number of times, the trick here is to try to develop a set of statements that, or a sequence of statements that you can do exactly the same way every time. And so to move us towards that, what we really need to do is somehow figure out a way to make all of these terms, and I'm gonna include the operation here, look identical, right? And so the first step I'm going to sort of exploit is that 1 is just 1 over 1, right? So now we have 1 over 3, 1 over 5, 1 over 7, 1 over 9, 1 over 11, oops. And we can see the numerator is clearly increasing by 2. And we can almost start to think about creating a formula where we have 1 over a denominator. And then each time around the loop, we're doing denominator plus equals 2. But we need to deal with this sign. And one thing that we can notice is that writing it this way is fine, but we could also write 1 plus negative 1 over a third plus negative 1 over a seventh plus negative 1 over 11. Okay, so now this becomes always a plus in front of it. But we have to count for this sign. And what we can do is we can multiply 1 times a sign, which is either 1 or negative 1. And how do you change from positive to negative to positive to negative to positive to negative? Well, you multiply by negative 1. So each time around this loop, we can increase a denominator by 2. We can multiply the sign by negative 1 to flip the sign. And we can add or accumulate this term. So let's put that to code. I'm going to ask the user for how many terms they want. And now I'm going to generate a sequence of these terms. I'm going to initialize sign to be 1 and denominator to be 1 because that was the first term in our sequence, right? Sign is positive, denominator is 1. I'm going to go around the loop n times. And each time I'm going to generate a term. Right now, let's just print out sign and denominator, because I want to make sure that it's the right value each time. And I'm going to multiply sign by negative 1, and I'm going to increment denominator by 2. And let's just generate 5 terms. If we look at my pattern here, I've got positive 1 over 1, negative 1 over a third, positive 1 over 5, negative 1 over 7. This is the exact sequence that I'm looking for. So we've got the right terms each time. From here, it's really just a simple accumulation. So answer equals 0. Instead of printing out sign and denominator, I'm going to increment answer by the result of sign, and doing 1 times sign is probably not really necessary, divided by denominator. Now, when I'm all done, I can just multiply the 4 times the answer, right? Because in our problem description, remember we had a 4 being multiplied at the end. Okay, so with 5 terms, pi is approximately 3.3. And the question is, well, is this right? Right? I don't know, because I mean this is an approximate estimate. We thought about some of our test cases, like if we had 1 term, pi is 4. If we had 2 terms, pi is 2.6. We're bracketing pi, right? We're going above it. But clearly we're going to need a lot of terms actually to make this work. We can kind of get an idea of how close it's getting by printing it each time. So I'll print out 4 times answer, and let's run it, and let's run it with 20 terms. Okay, so we can see the list of terms that are being generated, and we're getting closer and closer to the value. Let's run it with 100. All right, 100, I'm getting 3.15, 3.13. Still not really within 100th. 1,000 runs fairly quickly, got 3.14. 10,000, we're getting 3.14, almost 1.5, so it's bracketing to 1.5. If I try 100,000 times, it's going to go for a while here, but we're getting fairly close. We got 3.1415 now. Right? And so you can get an idea of how many terms we actually need here. 1 million is going to be probably pressing our patience a little bit, but it's going to start to stabilize on that 5. You can see that's happened now. I probably should have printed out which iteration we were on so I had an idea of how long this was going to go. Let's keep this over here. But as that runs, I want to point out that I could probably speed this up if I don't print things out. So this is kind of trying my patience now. Notice I do have out to 3.159, so that's a pretty decent answer, but I haven't stabilized on that last digit. Let's run this a million times without the print and see what ends up happening. You saw that it almost, I mean, there was a little bit of a delay, probably like a half a second, but we got our answer pretty quickly. Remember that printing is expensive. The act of actually printing everything out each time around a loop actually was slowing our program down pretty significantly. Certainly, we'd have to go out to, hundreds of millions, trillions of terms to be able to continue to get pi out accurately across many digits. But it's not too bad, right? It goes pretty quick if you're not printing. And in computer science, we do have, of course, better algorithms to get a more to converge on the answer, or to converge more quickly towards the answer. But this is pretty representative.